absolute. So absolute convergence is that, well, talk about a normal from 1 to infinity. Now, if this is going to converge absolutely, then the absolute value. So in order for the regular function to do what we call converge absolutely, the absolute value of it must converge. So it makes sense. If the absolute value can converge, it converges absolutely, or we have absolute convergence because the absolute value does. Great naming techniques, right? So this will basically apply to alternating series. So if you will remove the alternating part, does the function still converge? So for example, -1 to the n over n squared. The value of that, we're going to get just 1 over n squared. Where our p is equal to 2, which is greater than 1. Therefore, it will converge. So we can say that our setup here will converge. Absolutely. On the other hand, so we do this one. And once we take the absolute value, we get this. Because it's the harmonic series. For which, by the way, to show that this converges even, we should use our alternating series test, but it does converge. So this one will converge what we call conditionally. Are series that just diverge, the ones that alternate, sometimes they don't always converge. They could converge absolutely. Formally, this will converge, but the absolute value of it will diverge. And if we get this set up, that's what we mean by converge conditionally. Next one, it seems kind of obvious. We have some series. converges absolutely. It will converge. Now, it seems pretty obvious, but when we're doing our absolute convergence test, we're not looking at the regular summation. We're looking at the summation of the absolute value and saying that judging whether it converges, but if the absolute value can converge, then the normal one will also converge. All right, let's try next one. Next test we're going to do is something called the ratio test. And now, what our ratio test is going to do is we're going to take the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. And then we're going to get some value L. Now, it's an absolute value, so it's never going to be negative. But now, depending on what that L is, we're going to be able to make a determination about what's greater than z, excuse me, greater than 1, then our summation will diverge. If L is less than 1, then our series will converge. It will converge. Absolutely. So it's a stronger test. We're not even going to be able to say, not even just saying does it converge or not, it will converge absolutely or diverge. Then our last option is if it equals 1, as the motorcyclists drive by, then it's inconclusive. So we cannot say anything about the series. We don't know if it converges. We don't know if it diverges. We need to use a different test. So that's the important thing. It was not one that we were looking at. It was 0 or infinity. It was only went to a number. Here, it's 1 that is going to be our deciding factor. So let's try one of these. Let's say we want the series. -1, the n, n cubed over 3 to the n. Now you're going to see a lot of these for the ratio test and for the root test that we do coming up here that are have this alternating part. Now, typically that is a key giveaway of, oh, let's do the alternating series test. But there's going to be some other details and other things you want to look for that are going to make you be able to recognize that the ratio test might be a better option. So once we go through all the tests, we'll give some strategies of, okay, here's your situation, here's your best test. Here's your situation. Here's your best test. So let's do our limit. Absolute value. Make all of your n's n plus 1s divided by just have your original function. Here we are dividing fractions. Don't forget the absolute value. Make sure that stays around here because that's going to be important. So now, the nice thing with a lot of these is anytime you have these exponentials, the 3 to the similar situation that the n plus 1, or well, the negative 1 to the n will cancel the bottom. We're still left with just a negative 1. And then we're going to have to do something. But let's rewrite this. We have that negative out front, and we can make that a 1/3 if you'd like. And now we only have this n plus 1 cubed over n cubed. Now with this, nothing to do with n's, so we can pull that out front. And since it's an absolute value, that's going to just become a positive 1/3. Factor out an n from inside the parentheses. Therefore, whenever 1 plus 1 over n, all cubed left over, and then our n cubed, which are going to cancel. All right, so now we have an easy limit to take. Our 1/3 is going to stay out front, and then this part will go to 0, so it's just going to be a 1. So it's 1/3 times 1, which is 1/3, which is less than 1. Therefore, we have convergence. Let's try another one. N equals 1 to infinity of n to the n over n factorial. So for anyone who's unfamiliar with it, n factorial is n times n minus 1 times n minus 2 times, and we keep on doing this till we get down to 2 times 1. So we start doing a bunch of multiplication. Let's do our ratio test. And by the way, we should the test up above as well. So n plus 1 raised to the n plus 1 all over n plus 1 factorial divided by n to the n over n factorial. Now I mentioned before for the limit comparison test that order did not matter, which one was on top, which one was on the bottom. for the ratio test, absolutely vital that we have things in the correct order. So the n+1 stuff has to go on top. All right, so n+1 raised to the n+1 times n factorial over n to the n times n+1 factorial. Now simplifying things, this n+1 factorial is n+1 times n minus 1 times n minus 2 and on down. So basically it's n+1 times n factorial. So the factorials cancel. So now for our other stuff, how do we simplify that? This top is n+1 times n+1, the n power. With our n to the n, we need a way to manipulate that. So we have our n+1 times n to the n. Now, the nice thing here is those are going to cancel. And we could have just looked at it over here and we could have canceled that with the bottom two. So take your pick. But now, notice that both of our things here are raised to the n power. So we can combine them together in n+1 and n raised to the n power. Here, we can do a little bit of work of splitting things up. So that's 1 plus 1 over n inside those, raised to the n. And now this is a common limit. That when we take this limit, our answer is E, which is roughly 2.718. That's greater than 1. Therefore, we used our ratio test, and this one will let's do one more. And let's just do 1 over n. All right, we know that this is going to diverge. We could use our p-series, we could use our harmonic. Our ratio test on it and see what happens. If we factor out our n's, or we could do our L'Hopital's rule. This will go to 0, this goes to 1, so it's 1. Therefore, by our ratio test, this is inconclusive. So, something we'll find out later, the more you do these, anything that is primarily a rational expression inside of your polynomials or fractions of polynomials, do not use the ratio test. Now, expressions or terms that have exponentials or factorials, those are good for the ratio. First example was a mixture of a polynomial with the exponentials, so that's okay. But if it has nothing else other than polynomials, you do not want to use the ratio test. Next up is the root test. And the root test, we're going to do a limit as n goes to infinity of the absolute value of the, and they're going to put the, so the nth root of the absolute value of a sub n, just so we don't get any negatives in there. And this is going to equal something. And now our way of evaluating this is going to be exactly the same as the way we evaluated our root test, or excuse me, the ratio test. So we don't have to worry about any different conclusions. And if it's greater than 1, then our summation will diverge. And of course, it's going to be greater than 0 because since we're doing an absolute value, that's going to be a positive number. Our summation will converge. Absolutely. If it equals 1, once again, we are inconclusive. So when you're doing the ratio test, or excuse me, the root test, it's a key giveaway if everything is raised to a power. If it's not, then things can get a little bit sticky. So let's say we have 2n plus 5 over 3n raised to the n power. So again, everything raised to the n power. If we would try to do a ratio test, doing your n plus 1s here would make things very, very messy. Trying to do a comparison test, that power is going to kind of mess you up. Similar thing with an integral test. And no matter which of your comparison tests you use. So root test is the obvious choice. Of the absolute value our root and our power will cancel. We still have the absolute value hanging around. And then we can factor out an n or do L'Hopital's rule. L'Hopital's rule is probably going to be your quickest. And that's going to be 2/3, which is less than 1. Therefore, by the root test, this will converge absolutely. Next up, arrangement of our terms. And by rearrangement, we're meaning rearranging the order of our terms. So let's take this one. So we've dealt with this before, and we know that this will converge conditionally. Now, the actual summation of this does go to the natural log of 2. And if we write this all out, it's going to be 1 minus 1/2 plus 1/3 minus 1/4, and then so on. However, if we modify things a little bit, we can see that it goes to. Now we have to be careful with this. If something will converge absolutely, rearranging things will not make a difference. But if it converges conditionally, it can make a difference. So if we would rewrite this, where we would do 2 of the positives, then the negative, then 2 of the positives, then the negative. And we keep on doing that. We will still end up with all the same values because it's infinite. But the way that the order is structured, this gives us a different value. This would then be 3/2 natural log of 2. So an interesting thing here that for our conditionally convergent situations, that we can rearrange the terms and get different values as a result. If it's absolutely convergent, the rearrangement makes no difference whatsoever. And as a matter of fact, something that Riemann proved is that if we have a conditionally convergent series, you can rearrange the terms to equal pretty much whatever you want for any real number. Just a matter of finding the way to do it. Now, important thing though is we are concerned about mainly just convergence here, not necessarily what the value is, but the way that is written is going to be the official sum. And then we're not going to worry about the rewriting of them because that would technically change the way that formula is, which is why we get different values. But it's pretty interesting that if you have the same numbers just in a different order, you can get a different result.